Guys, just make this official right now. Quizzes. Next week. So at least Monday and Tuesday. So Monday lab. Tuesday's labs. And I'll let you know at the beginning of next week if I want to do more quizzes next week. Or at least you know about those. So these quizzes, let's see what is there, Wednesday. So 3.1 through 3.3. Let's see. Say again?
Today? No quiz today.
No quiz today, no.
Yeah.
Do you want there to be one?
No last minute.
Believe me.
No.
I always make the quiz up. Alright. So we got that? Okay. If any of your friends are not here and you're a nice person, you have to know that. Alright, so pretty much last time, I think we ended up talking about this guy. I do like giving this kind of problem. It should be relatively easy. You don't have to find the Y-intercept and the X-intercept by calculations. You just find what they are by what somebody did. Now, I want to go one step further on this kind of problem. Real quick on this problem, what is the Y-intercept? Yeah, let me zoom in a little bit. This is page 41. Yeah, 0, -6. Right? The creative geniuses that are the mathematicians of old, they're like, it hits the y-axis, let's call it the y-intercept. I mean, so it makes sense. I should be making fun of them because sometimes we don't name things very good. We don't use English very good either. What about the X-intercept? Careful. I heard somebody in the back. -2, 0. I like it. Because X is -2 when Y is 0. I love it. That's really how you read a point. X is this when Y is this, or Y is this when X is that. Either way. I like it. Maybe. Let me go one step further. Looking at this graph, let me pick out. Oh. You don't know what this line equation is. Some of you guys might be able to figure it out, but and later we're all going to learn how to do it. But let's say we don't know what this line equation is. But can somebody tell me, if I put a -4 here, what would go here? Yeah, I hear the right answer. I like it. What does this mean? This means when X is -4, Y is 6. And I don't even need the equation to know that because the line represents all the work. Somebody's already done all the work. You guys see that? You guys see that? I can. If I have the graph, people freak out. What's the equation? It doesn't matter. Somebody's already done the equation, figured out all the answers. So I can ask you a question like this, and it's beautiful. You don't have to do any work. You just got to look. Where's the point? Do you guys see that? This skill that I just discussed, not a very intensive skill, right? Just takes a little bit of a realization. Probably my pre-calc students, when I go over this, they're like, what the shit just happened? But it's not a big deal. When X is this, what's Y? You just got to look to see where the point is. I like it. So this would definitely be 6. I like it. Yep. Just a little side note. You can't kind of see that in your homework. Maybe you'll forget it, but later it'll come back. Now this is kind of funny. How do I graph y equals 3? And I have to be very specific when I give you a test or something. I have to tell you to graph it in 2 dimensions. Why would somebody have trouble believing that should be in 2 dimensions? Because how many letters are in that equation? 1. So before, when I said graph x equal 2, you would just put a circle on 2, right? Put a closed circle on 2, and you'd be done with it. But I'd have to tell you do it in 2 dimensions if I wanted that. So what the hell, y equals 3? What would that look like? Well, we can do it very systematically, and then I'm going to tell you the shortcut here after we do this systematically.
Well, it's gonna be horizontal because it's Y. Oh, sorry.
You're good. I like it. So it will be horizontal. Why the hell would it be? So the equation says y is 3. So when x is 0, what's y? 3. When x is negative 2, what's y? 3. When x is 18 million, what's y? 3. I'm not going to graph that last one. So if I plot the points 0, 3, 0, 3, and negative 2, 3, negative 2, 3, I can connect those with a line. And then, of course, if you start to realize what that equation means, I think I talked about this a little bit before. Y equals 3 means y can't change. If y changes, what way do I move? If I change y, what direction do I go? Vertical, like up or down, right? Make y bigger, it goes up. If I make it smaller, it goes down. If y has to stay at 3, that means it has to stay at the same level. And remember, when we talked about this before, I said, what does x have to do? Well, x can be any damn thing. See how x is every number? Does negative 5 x do? Yeah, it goes to 3. Yeah. But y can only be 3. So what would x equal to 2 look like? X equal to 2. If x has to stay the same, I can't move left and right. I can only move up and down because y can do whatever the hell it wants to do. So x equals would be a vertical line. Y equals would be a horizontal line. That's the whole point of this little section on page 41. Whee! Horizontal and vertical lines. So horizontal would be y equals a number. Vertical would be x equals a number. Okay. And another way to look at this, since there is no x in this equation, will the equation change if x changes? Will the outputs change? No, they don't give a crap what x is. We're 3. Right? So it just stays there. It's sort of like, said, how high up the ground is this book? Maybe 3 feet. Now wait a few seconds. Now how high is it? Still 3 feet, Jeff. It's just flat until you do something. All right. Maybe. Okay, so don't let these... Now, these are going to trip people up, because if you try to force them to work the way that just everyday, like x plus y equals 2 lines work, they're not going to work that way. Their slopes are going to be weird. Everything's going to be a little weird about these special cases. Unless you remember the special cases, and then they're easy. They're just their own case. So we're going to look at slopes here in a little bit. Okay. Well, here they are. In general, a horizontal is y equals a b. B is any number you want it to be. Vertical line is x equals a. So the bottom of page 42, what's that equation for number 3? Don't say anything for a second. Don't say anything for several seconds. Think about it. The number 3. All right, so now you can tell me, what's the number 3 equation? Y equals 6. Y's got to be 6. Do I care what x is? No. And of course, what would number 4 be? X equals negative 5. PCAS. I love it. I like it. So if x and y are both in the equation, can you see what I mean when I say it's going to be diagonal? The line will be diagonal. If x or y are missing, it's going to be some just straight across or straight up and down.
I didn't get that.
So if x and y are both in the equation, like x plus y equals 6, or 2x minus y equals 7, whatever the hell. If they're both there, the line is going to end up being some kind of diagonal line. If one of them is missing, it's either going to be that guy, I wouldn't call that diagonal, or that guy. Otherwise, it's somewhere in between those things. Does that sort of make sense? Do you have to totally understand what I just said to do it? No. But if you really understand it, that means you get it a little bit better. Okay, so this will be y equals 6. This will be x equals negative 5. Gas. So if you remember that they're special cases, they should be easy. Pretty easy, yeah. Not always. Okay. I sort of like and don't like that they do this. So it should be kind of obvious if you rent a bike and it's like so many dollars per hour, right? Really? Dollars. So the amount of money you pay should kind of like continuously increase. If you take it out for longer, you should have to pay more money. So that's the idea behind this. Can somebody figure out, can you look at the graph, not even doing the work there. Look at the graph, can somebody figure out how much per hour it is?
For 1 hour?
I like it. The scale is a little funky, right? What's the scale here? What would this be?
8. That's 4.
4,
12.
8, 12. I like it. So after 1 hour, how much did the person have to pay? $8. So it's $8 an hour. Sure enough, after another hour passes, if it's $8 an hour, where should it be? The cost? 16. Oh my God, I love that reaction. Sure enough, it's a freaking 16. Right? So that is actually, if you've seen it, most of you guys should have seen the idea of slope before, but this idea of slope is rate of change. Slope is how much does my y change versus how much does my x change. And let me give you an example from everyday life. Anybody ever done much driving? Interesting thing about, you're like, shit, yeah, man. I live in, some people live in like Escondido or something. Yeah, you do a little bit of driving. Have you ever seen like runaway truck ramps? Anybody ever seen it? I remember the first time I saw that, I was like, okay, this is different. And I'm like, looking up, oh, shit. And why do they have runaway truck ramp signs? When is that going to happen? When the slope of the road, when the grade, what's called the grade of the road is huge, right? Or relatively huge. So somebody ever seen a grade sign on a road? All right, can you remember about what percentage it was? 7%. That's a typical one. I like it. There's some hill. I used to live out in Mission Hills, and there's this one street that I swear to God, it must be 8-9%. I don't know if anybody knows the street I'm talking about. The people that live on this street, I'm like, holy shit, you guys must be in cabs out to nowhere. All right. What is 7% as a ratio? 7 over 100. So when I see 7% grade, what that really means is every 100 feet you move forward, and let's pretend like this is going up the hill, right? I go up 7 feet. Now that doesn't sound like much, but a normal road is 0, right? So it doesn't take much. 7% grade. Every 100 feet you go up 7. That is 7% grade, and if you've driven, 7% grade is a decent slope. That's when you start having runaway truck ramp signs, right? And brake checks and all this kind of shit. Like it maybe. Some of you guys are like, I've never driven. Do I have to drive to know math? No, man. But hopefully that makes sense, the idea of that grade. Let's see. Oh, so let's look at this example here. If it took Susie 18 hours to read 6 chapters, her average rate was 3 watts. Now here they're talking about units. Now where do they get to 3 from? How do you figure out her average reading rate? Yeah, they did something kind of weird here. They did hours divided by chapters, right? So it'd be 3 hours per chapter. Yeah, I know. Something, I don't know. I'm going to give her the benefit of the doubt. It's some kind of, it's in a different language or something. 3 hours, or the chapters are like 17,000 pages long. 3 hours per chapter. Now, I agree with some of you guys. What would be the more normal kind of rate to make? Yeah, well, if I did it the other way around, chapters per hour, what would that rate be? It would be careful. It would be 6 chapters per 18 hours. So if I did 6 chapters per 18 hours, what does that reduce to? Yeah, so it'd be 1/3 of a chapter per hour. Which is why it's 3 hours per chapter. So you can get 1/3 of a chapter per hour. I like it, maybe. You could do rates either way. Normally we do miles per gallon, but you could do gallons per mile if you really wanted to. Per mile. Now, if Jeff, yeah, I see these sidewalks and there's bare, and I'm like, I gotta get me some petunias out here. So, Jeff, if I planted 48 petunias along a 12-foot sidewalk, now this is interesting. The average rate. Normally, when you read that, you think about time, but this is actually kind of a length rate. So, what they do to get 4, they did 48 petunias. Petunias, what a weird word. Divided by 12 feet. So I put what? I put 4 petunias per foot. That word petunia just really, the more you say it, it just gets weird. Petunia. 4 petunias per foot. So on one level, this should be not that difficult. You're just making ratios. This is like back in Math 88, you did this kind of thing, but we're doing this just to remind you guys and then to tie it into what slope is. Blah, blah, blah. All right, let's look at number 3. You guys, ooh, I like it. Read through that and try to do these 2 problems here. So let me see. Setting this up isn't too hard. It's figuring out how I might want the answer given to me. But what's the beginning ratio I can set up here? She went how many miles?
17.
She was at mile marker 17. And then a bit later, she's at mile marker 23. So she went 6 miles.
Oh, hello.
So she went, and this is miles per minute, right? So she went 23 minus 17 miles. So she went 6 miles. In how many minutes?
45.
Yeah, 3:45 minus 3. That's kind of a weird calculation. 45 minutes. Now you could reduce that, but it's still kind of a silly. I'm not going to say something to somebody. My rate was 6 per 45. No, I would just make that into a decimal. Oh, at 3 o'clock she was here. At 3:45.
Okay,
Yeah, so 45 minutes later. I like it. So what's 6 divided by 45?
0.13.
0.13 forever?
Yeah.
Okay. Miles per minute. All right, that sounds like getting around San Diego sometimes. 6 miles in 45 minutes. Now, part B shouldn't take anywhere near as much work. What do you do to get part B? I want minutes per mile now instead. Yeah, I take this guy and flip it. 45 minutes per 6 miles. And what's 45 divided by 6?
7.5.
7.5. 7.5 minutes per mile. That's slow for a runner. All right, how are we doing so far? Is that? All right, so that shouldn't be too big of a deal. And we can turn ratios around and make things that we're not used to, but mathematically it still works. Ooh. Okay, let's do number 4 together here. So I don't know if you know Nemi Tapasia. She's teaching the 110 version of this right now. So on February 1st, Nemi rented a Honda Accord with a full tank of gas and 8,452 miles on the odometer. You're like, oh, I like this problem already. On February 7th, And then we returned the car with 8,890. So I can see several rates of change. How the days change, how did the odometer change, the mileage change. If the rental agency charged NEMI $324 for the rental car, including the cost of the 12 gallons of gas needed to fill up the gas tank, find the following rates. All right. The car's rate of gas consumption. So when you get a rental car, what can you do? You can either remember to fill the tank up, or you can bring it all the way back and go, shit, and then have to actually pay, and it's always some stupid number, right? If you've ever rented a car and you forgot to fill up the tank, yeah, it sucks. So what do I need to know to be able to create this ratio? Well, they give me the ratio. It's miles per gallon, right? So I got to know how many miles did she actually go. Yeah, so the mileage was 8,890 minus 8,452. That's the miles. And of course the gallons, 12. Yeah, when she gave it back, it was full. When she gave it back, they had to fill it up with 12 gas. So she used 12 gallons of gas. Exactly. That sounds like a math person to me. So the bottom is 12 gallons. Miles per gallon. I love it. So then whatever the heck that is. Yeah, 438 divided by 12. 36 and a half? MPG. Sounds about right for a well-maintained Honda Accord. My car just dreams of that number. So what do you need for part B?
324.
Yeah, it costs $324. Now this is kind of mean. It's kind of evil. It's kind of like if you've ever rented a car, you know there are rules for when to count a day against you or not, or kind of like against you. But let's just assume that it is going to be, let's see, if she did it on February 1st, February 2nd, February 3rd, February 4th, February 5th, February 6th, February 7th, technically be 7. Right, so the problem doesn't even give us enough information for this. But let's say it is 7. What would that be? 46 even? 46.28.
Yep.
And what is that? 46.28 dollars per day. I like it. Now please don't freak out about the whole thing about the days that just occurred. I'm not going to make this into day math kind of work. Day math. Fight chicken for night math. And then a car's ready to travel, miles per day. How many miles? We already know that, right? 438. How many days? We figured out it must be 7. $62.57. Who's per what?
Miles per day.
Miles per day. Sweet. Sweet. Okay. So a lot of that is not, it's not algebra yet. That's just pure, can you work with these numbers that they give you? The point they're trying to make is that when I have a visual, I can see what I need. So at what rate did the train travel? We're going from Denver to Kansas City. Sounds like we're following a football team. And they give me a couple points here to make it easy. Maybe. These points kind of suck. Oh well. I could probably pick some better points, but I can't. Here. See this point right there? Do you see why that's a better point?
Because it's on the line.
Because it's on both lines there. Does somebody see it? Well, actually, this one wants to be on both lines too. That's kind of crazy. Probably. probably isn't quite. It's almost there. Let's see, what is this point right there? What would that point be? Here, it would be 3. Well, it's between 300, 250, 275, exactly. I like it. Feel a little bit like an auctioneer there. And then this one looks to be 5 o'clock, right?
Yeah.
5 o'clock. 450. I like it. So really, the idea of slope is how much did we climb or fall as we went how far over, right? So it's I think a lot of you guys know the phrase for slope. It starts with R's, right? Rise over run. So how much did we rise here? What would that be? How much did we rise?
25.
That's the difference in the distance, right?
25 miles.
450 minus 275.
It's 25.
Yeah. So 450, not 25. 450 minus 275.
175.
175. And what about how much did I go over? How many hours did that take? 3 to 5? 2 hours. So we went 175 miles in 2 hours. So what's up? Everybody all right? So again, this is actually the same exact work we did up here. It's just they gave it to me in a visual format. So I can now see it. How much did I increase my distance and how long did it take me to do that? To make that ratio, that's going to be miles per hour. And then what's 175 divided by 2?
87.5.
And that'll be, where do you go? Miles per hour. I love it. Okay. That's that section. That section is purely about rates. They don't even call them slopes yet. They just call them rates. Last thing I want to do today. You guys are already looking at that clock again. Please don't make that. I know there are a couple little freaky spots in some of these problems. I promise that will not always happen. This little day thing I'm thinking about. The idea of rate is pretty straightforward. I mean, if you go to try to get an office job and you type 200 words and it takes you 3 minutes to do it, how many words per minute will you do 200 divided by 3? That's your rate. That's your typing rate. Now slope, thank God, is exactly what we think of in physical life. What do we think of as slope in the real world? Well, hopefully the floor would have what kind of a slope? Would it have a big slope, the floor? That would be difficult, right? The slope of the floor should be 0. It should be flat. It should have no slope to it. And now if I'm going to climb, if I'm going to go, what's called, what's my little brother? So crack climbing. Have you ever heard of crack climbing? You got cracks in the rock and you just hold on to it. And don't take that some other place. Right? It's not talking about how you prepare for the climb. It's the cracks in the rock, right? If you want to go straight up and down, that's going to be holy shit slope. Right? That's going to be what we call, does anybody know what that is if it's straight up and down? Sure, but what's the slope? Infinite slope. That's what we call that. I like it. So now let me ask you this. Let me talk about some things we see in everyday life. Why do we have ramps? Why do we have like handicap ramps? So it's easier. So the slope is decreased. Has anybody ever went up Cowles Mountain? Or Coles Mountain, if you prefer to call it that. There's two kind of sides. There's two sides to go up. One side is almost just straight up. And the other side, there's a lot of switchbacks. Right? So the switchbacks, what are the switchbacks trying to do? Trying to decrease the slope. If you just went straight through all the switchbacks, which some assholes try to do, stay off of there. Restoration in progress. Do not do this shit. But if it did go that way, the slope would be a lot bigger. I guess it would be. So a handicap ramp is trying to do the same thing. Instead of going up these steps that go up in very little time, ramps go up the same amount over a much longer time. So for example, I get to try this out. So if I have a stairs leading up to a little door versus a ramp on the other side, let's say this is 4 feet and 3 feet. And let's say for the ramp, it's 4 feet. But in, let's say, no, 10 feet. So what's the slope of this? What's the slope of this? The average rate of increase in your height would be 4 feet per 3 feet. Right? 4/3. What about this side? You go up how much? 4 feet. But you do it in how long? 10 feet. So this would be 2/5. So this slope is much smaller. So thank God, the idea, if I mathematically find the slope, the lines we graph will visually have exactly what if I have a very small slope, it's going to be like this. Whereas if I have a very large slope, it's going to be like this. So thank God the idea of slope in math matches the idea of slope in real life. Happens more often than we realize, but this is a little more in your face. They exactly line up with each other. Okay. So here, this is sort of like the one we did last time, but now it's not related to any units. They don't worry too much about units right now. They just want the slope algebraically. Another way I think of slope is, if I have a straight line, let's say there's a straight path leading somewhere. If I wander off the path, the slope will always get me back to the path. So what do I mean by that? I mean, if I want to get here and I go up to here, how far off the path am I? Well, I went 1, 2, 3 up. How much over do I have to go to get back to it? 3. So this slope would be a rise of 3. And I'm going back 3. So slope is rise over run. So if I start at this point, I go up 3, and I go back 3. So up 3, back 3. This one has a slope of -1. Now somebody could argue, what if I start here and go there? Well, this is a straight line. Can the slope change? If the slope changed for a line, if the slope suddenly started to change, what would the line do? It would start to curve. I love it. So have you guys heard of a math course called calculus? All calculus is, and I'm not actually trying to downplay it because it's not like easy, but all calculus is, well, can we still figure out what the slope is if it starts to do some curvy shit? Lines, once I know the slope, I know the slope everywhere. It's always the same slope. Calculus just says, well, here the slope is just always changing. That's enough about calculus. It's okay. Just remind yourself, you don't have to do it right now. Yes?
So do we all, I started at the point in the middle, and then I got 4 over -4, and then still it gives me -1.
Beautiful. See, that's what I was about to do. And let's actually start up here. How would I get down here? I go down
-4.
4, and I would go in the positive direction 4. So if I do this, down 4, 4, -4 over 4 is still -1. Same slope. And if you think about it, it only makes sense. It's the same line. It's a straight line. The slope can't change. So it doesn't matter which 2 points you use. I like it. This should sound a little familiar. Now watch. Now, I'm not always going to have the graph, and I don't want you guys to always have to graph the points. You should be able to get it algebraically. And I sort of got you there with what I was doing here. So right here, what's this point? What's the coordinates of this point? 3, -3. And what's the coordinates of this point here? That's crazy. So how much does it go up would be how much do the y's change, right? Oh shit, you guys know where this is going. So how much do the y's change? Well, they start at -3 and go to 0. So 0 minus -3, oh shit, over 0 minus 3. This is 3 over -3, which is still -1, yay. So the whole idea is if I rise, what letter changes again? Y. And the beautiful thing is, guys, the beautiful thing is slope is rise over run, which is the difference in the y's. Notice how y's rhymes with rise. Shit, right? Over the x's, what I call the other guy, so it still kind of rhymes. So it's going to be, in general, if I just have some line somewhere with some points, can somebody tell me what that point is? No, good. But I'm going to call it x1, y1. Why would I do that weird shit? Because that's the first point I pointed to, so I'm going to call it the first x and the first y. So what's this one going to be, amazingly enough? x2, y2. That's insane.
Is this where you do the
Ooh.
y plus y1 plus y2?
Almost. I want the change in them, though. I want the difference in them, so it's going to have to be minus. I want to see how much did they change by. So that's why the formula is right there. y2 minus y1 is how much it went up or down. x2 minus x1 is how much it ran forward or backward. So this formula is the same thing that we did here visually. So if I give you a visual, don't use this formula. You can just count up and over. If I give you points, like probably on the next page, this one. Oh, real quick, did I tell you why the slope letter is M? You guys know this, right? The slope letter is M, mx plus b. It's, why the hell is it M? M is not in the word slope at all. So, what the hell's wrong with you?
So it looks like this.
It's from a French word, marcher, meaning to walk.
Why didn't you tell us?
I did tell you that, okay, good. But you forgot already. Man, they're really stuck in there. It's like, I don't need that to pass this test, so it's gone. So M is y2 minus y1 over x2 minus x1. I really want you guys to understand this. The subscripts kind of throw people off. The only real reason I need the subscripts is because if I subtract one way with the y's, I have to subtract the same way with the x's, or else my slope is going to be the wrong sign. So if I do 2 minus -1, do you guys see that? The y's. If I go 2 minus -1, I have to go -5 minus 1. I can't just do that whatever order I want to, because that would change what the slope is. It would make it the opposite sign. That's really the only reason they exist. Now, if you want to, you could call, like in this example, I called this one x1, y1. This one x2, y2. You can just do that. You can call one of them x1, y1. You can call the other one x2, y2. And then the top would be y2 minus y1, bam. y2 minus y1, x2 minus x1, bam. The other big mistake people make is related to negatives, of course. Negatives always find a way to get us to make a mistake. People will write 2 minus, and they're like, I already wrote a minus. Why do I need another minus? Because it's a freaking negative number. That's why. Right? It's y2 minus y1. Well, if y1's negative, it's got to have its own negative. And then, of course, what happens on the top? Yeah, these become plus, so you get 3, not 11, Jeff. 3 over -6, which is -1/2. Kick ass. Now suffer with me just for a little bit longer. You're like, that's all we do, Jeff. Let's plot these points. Where's -5, 2? There's -5, 2. And where is 1, -1?
Over 1 down.
Yeah, over 1 down 1. I like it. quadrant 4. I love it. Kick ass. Yes.
Well, I got -3. I know it doesn't matter, but I got -3 over +6.
Okay, now watch. So did you do this instead? Did you do -1 minus 2,
Yes.
-1 minus 2, then you have to do 1 minus
I
-5.
just did 1 plus 5.
Good. So -3 over 6, which is still,
-1.
Yeah.
Okay.
so that's what I meant by the subscript only exists because if you subtract one way the y's, you guys subtract the same way with the x's. Because it doesn't matter which one you call the first point and which one you call the second point. That's arbitrary. But the only reason they're in the equation is it's saying you've got to subtract the same order.
Okay.
You guys with me? Yeah, I think people don't tell people this, but I want you to realize that's the only reason we have those stupid little subscripts in the equation is because, holy shit, you got to do the same order. That's all they mean. So now watch. Let's see if I can do this well enough. Probably not, Jeff. Now I want you to see something. This is really neat. When slopes reduce, sounds like a really, really bad TV show. When slopes reduce, so look, down 1, 2, 3, right? And over 6. You with me? Ooh, that's amazing. But look, it reduced to -1 over 2, didn't it? So if I go down 1 over 2, oh, I'm back on the line. Down 1 over 2, oh, I'm back on the line. Do you guys see that?
Yes.
Okay. And then I could do like 30 over 60, to be honest. Go down 30 over 60, and I'd be on the line again. It's crazy. So any multiples of top and bottom of the slope will still get you back to the line, just further down or closer. Littler steps or bigger steps. Okay. All right. Not too bad, right?
Do you want the reduced answer or just the regular?
Always reduced answer, right? I think that's funny.